All right, good afternoon again, everyone. I'm Mike Toth, the Director of Research at Civitas, and I'm going to get us started with our first esteemed panel. We're going to be talking about the 2025 DoE report, and this is a report that was commissioned by the U.S. Department of Energy. We have a link to the report on the website and the conference materials. Commend everyone to take a look at the report if you haven't already. We've got four excellent panelists. I'll do the very brief introductions, which won't do justice to their incredible accomplishments. We've got Steve Koonin, who's the Edward Teller Senior Fellow at the Hoover Institution at Stanford University. We've got Ross McKitrick, who's a professor of economics at the University of Guelph in Canada. We've got John Christy, who's a climate scientist from the University of Alabama. And we've got Dr. Andrew Dessler, who's a professor of atmospheric sciences at Texas A&M. There it is. And the director of Texas's Center for Extreme Weather. And Andrew and I joked he brought extremely good weather today from the Center for Extreme Weather. This panel has a really innovative setup in terms of the presentation. So we're going to sort of do this as three different segments. So the format is going to be Dr. Christy is going to start by talking about extreme weather, and Dr. Dessler will provide a response, and then Dr. Koonin will talk about modeling, climate modeling. Dr. Dessler will provide a response, and then Dr. McKitrick will talk about economics and climate with a response from Dr. Dessler. All of that will take about 40 to 45 minutes, and then at that point we'll open it up to Q&A. So again, the point of this conference is really to make a dialogue. But for purposes of this panel, we just ask, we do want to do question and answer, but we ask to kind of hold it until the panelists have sort of worked through these three main topic areas from the DOE report. So without further ado, Dr. Christy, the floor is yours.
Thank you, and thank you all for coming out on this day. And we're going to talk about a section of the report I worked on quite a bit was extreme weather. And is it changing? Are the extremes in weather changing here in the continental United States? We call it the CONUS. And so this is the final version of our draft report that basically said there is no statistically significant changes in the extreme weather throughout the United States, whether you're talking about hot days in the United States compared to the earlier times, or storms, hurricanes, tornadoes, no long-term increases. Extreme precipitation events, don't see those persisting in terms of change throughout the country, and wildfires are not more common than they were in the past. What you will see here are actual data. I've got to emphasize that we built actual data sets to do this. So, for example, for the temperature in the United States, we looked at 1,211 stations across the country, all started in 1899 and all finished through 2025. And this is what, if you ask the question, when did record high summer temperatures or record low temperatures occur in the winter, you'll get this chart. And you can't get any other chart from the actual data. This is what you get. And you see the 30s dominate with a lot of high temperature records. And there's a bit there in the 50s, and in the early 2020s, there's also some. Low temperatures have gotten warmer through the years, and this is throughout the United States. We see less cold extremes. If you look at heat waves, this again is the only thing you can get from the actual data. We see the 1930s are very prominent in terms of heat waves, a bit there in the 1940s. It turns out that when you talk about dune activation events or dust storms, or dust bowls, I should say, we had two in the 20th century, only two, the 1930s and 1950s. The 19th century had 7 dune activation events. So these are common features of our climate, especially in the Great Plains. When you look at heavy precipitation events, we focused on 3 areas in the report because those were areas that had been claimed to have changes in precipitation. But we have 9 areas now that we're looking at. And precipitation is a strange metric, but here is one example. This is Kerrville, Texas. This is the actual form that the observer filled out. If you look at July 1900, you see there on the 15th of July, 11.6 inches in one day. That was the heaviest event that ever occurred in Kerrville. It is not in the official archives of the of the federal government because this form was never digitized. We digitized all these forms so that we have a consistent and serially complete record of events like this. In fact, if you look at this, you'll see a severe rainstorm occurred with the Guadalupe River rising 33 feet. You might recognize that number from what happened last July. Precipitation, as I said, is a very erratic metric. The blue lines are the heaviest two-day precipitation totals in Austin, Texas. And you will see that in 1921, 19 inches of rain fell in 2 days. The second place is about half that. So this metric is, let's say, extremely erratic and chaotic, and applying statistical analyses to these has to be done with great care, because you can get any kind of answer just by adding a few more years and finding a few more extreme events. So this is what we did for the 9 regions. These are time series of the actual amount of rainfall that fell in the heaviest 2 days. You'll see the top line is the Northeast, and there's kind of a rise up to about 2009, and then it has fallen back. That was due to an extra surge of tropical activity during about a 20-year period, but that's no longer there. The rest of the time series really don't have much of a change. And in fact, if you look at the Texas Hill Country time series, the black one there, the lowest amount of heavy rain events has occurred in the last 7 years. So just look at the bottom table here. These are some examples of the statistical significance on trends. The bottom table shows the heaviest 1% of days. When did they occur? And is it significant over the whole time series? And the answer is not significant over the whole time series. As you can see, the 1980s have no trends upward. There's one trend downward in the Southwest. That's what the SW means. But if you start in 1958, which is the favorite year for the national assessments, you can get some statistically significant trends. But if you start earlier or later, you don't. And so you got to be careful then about how you have your data set, where you start and where you end. Global hurricane frequency, there's nothing happening there. It's actually slightly downward. And hurricane events, landfalling in the United States have not really changed. There was a very quiet period about 20 years ago. For 11 years, no major hurricanes struck the country, which is also the same time that the Northeast had those extra tropical cyclones. Tornadoes have been declining. Actually, major tornadoes have been declining. Droughts have not increased at all in the United States. We've gotten a little wetter, more moist. When you talk about global wildfire acreage burned, it's going down. And that's simply because people don't like their stuff to get burned up. They're stopping fires. In the United States, this chart is interesting. I wish we had time to talk about it. It's basically a 1,500-year chart of United States fires. And the fact we haven't had very many in the last 150 years from fire suppressions means we have a huge fire deficit. One little statistic to give you a clue about that is prior to European settlement, California saw 8 million acres a year burned. 8 million acres per year burned prior to European settlement. Today, the entire conterminous U.S. averages 8 million acres a year. So you can see that fire suppression is really a big story when it comes to global wildfires. And so I don't see anything in all the hundreds of comments I read about the DOE report that would allow us to change this statement. Most types of extreme weather exhibit no statistically significant long-term trends over the available historical record. Thank you.
Okay, all right, thank you very much. So I'm going to respond to what Dr. Christy said. So let's start with extreme heat. So this is a plot that was in the rebuttal, which I was a member of, and it shows basically the same things that Dr. Christy's plot shows. It shows this is days above 105 Fahrenheit. And I use that because it kind of shows it very clearly, but if you look at Dr. Christy's plots, it shows the same thing. It shows it's very hot in the 1930s. It shows it is, then we don't see a lot of heat in the middle of the 20th century, and then we see a lot of heat towards the end. I'm sorry, timer, so I don't go over time. And so the question is, what the hell's going on in the 1930s? Let me just ask you guys, what's going on in the 1930s? You guys know this. Dust Bowl, I heard Dust Bowl, exactly. The Dust Bowl. Okay, now, we know, we've studied the Dust Bowl. It's not due to carbon dioxide. It's due to some internal variability, and it's due to some land use changes, what farmers were doing. It wasn't good, and it generated these very regionally local, very local high temperatures. Okay, so then, what's going on in the middle of the 20th century? Why is there no heat records there? Well, again, people have studied this. And it turns out that it's because of industrial agriculture. They started irrigating. And we know irrigation cools temperatures. So you have the Dust Bowl, and then you have irrigation. Those are both human. Humans contributed, but it's not carbon dioxide. And now, temperatures are going up again. Okay, we know it's not a Dust Bowl, because there's not a Dust Bowl going on right now. You guys know what it is. What is it? Greenhouse gases, exactly. We understand the physics of this. Now, if you listen to what Dr. Christy said, it's a very calibrated statement. We see no trend. And that is true. You don't see a trend, but you have to look at the physics of the problem. You cannot just do naive trend analysis. If you look at the physics, carbon dioxide is clearly driving up temperatures. We understand what's causing this. So carbon dioxide, greenhouse gases. And I'm not going to talk in too great detail. This only works if you look at the US. If you looked at a different region, they wouldn't have seen the high temperatures in the 1930s. The Dust Bowl is extremely regional. This is the same plot using the entire northern hemisphere mid-latitudes. The Dust Bowl gets averaged out when you do that. And you see clearly carbon dioxide. So cherry picking a region dominated by non-CO2. I'm going to list what I call the scientific felonies. These are things that would absolutely destroy this from peer review. If you submit this for peer review, it would come back to you spindled, folded, and mutilated. Okay? It would not make it through. They ignore the physics interpreting the data. You cannot take data and just put a line through it and say, voila. You actually have to look at the physics. This is a continuing problem with the DOE report. They never ask the question, why do these trends exist? And if you ask that question, you will get quite a different answer than the DOE climate report did. They omit contrary interpretations, and they don't talk about the existing literature. Again, if a graduate student brought me that, I would say, where's your literature review? Where do you, why does the IPCC say, I don't know exactly what, actually, probably extremely likely that CO2 is increasing temperatures. Why are they wrong? We didn't talk about it, but Dr. Christy, he said something about using actual data. I think somebody asked him about it. We know the data he used, the USHCN data, has biases in it. They tend to warm the 1930s, cool present day. I think that's what he meant by that. It's a small effect, but just I would point that out. So lastly, this is truly a terrible argument. It is clear, any rational evaluation of the physics and the data makes it clear climate change is making extreme heat more extreme. All right? And again, this is absolutely, their argument could absolutely never make it through peer review. All right, let's talk about hurricanes. So the DOE report makes the following argument. So they say there's no change in number of hurricanes. That is correct. And in fact, the scientific community has never predicted there would be an increase in the number of hurricanes. So this is a straw man saying, they're making a claim that doesn't contradict anything the scientific community says. Wind speeds are getting higher. They do say that, and that is true, and that is bad. So hurricanes are getting more intense. Through gritted teeth, they acknowledge that. And then, in the very last section, in one sentence, they say, you can make an argument that rainfall should be getting more intense, but, there's no evidence for it. I can't remember the exact words they say, but basically they say there's no evidence for that, and ditto for increased total flood depth. That's wrong, and that's wrong. And in fact, let me just show you for rainfall. There's a lot of literature out there that shows that rain is getting more severe from hurricanes. And I'm not going to go over this, but I'll simply say none of this was referenced in the DOE climate report. And again, if you tried to peer review this, it would come back with like a footprint on it or something. That's what the reviewers think. I mean, you can't do this. You can't just say, we don't know this, when there's a lot of peer-reviewed evidence that suggests rainfall is getting more intense and storm surge is also, or the total flood depth is going up because sea level's rising, and the same storm on a higher sea gives you more total flood depth. So let's look at what the IPC says. And notice that the DOE report cherry-picked, another cherry-picking, you're going to see a lot of cherry-picking. They just talked about those things. Look at all the things they stopped talking, they didn't mention. Rapid intensification, that's likely. Latitude moving poleward, likely. Translation speed, likely slowing. Translation speed, those are very important. Rapid intensification, that is awful. Translation speed, that's how you get Hurricane Harvey. You have the storm roll over a city and just sit there. And they don't talk at all about the future. Now, we understand the physics of hurricanes, and we have high confidence they're going to get stronger in the future, or the percentage will shift towards stronger. We have very high confidence they're going to produce more intense rainfall. Very high confidence they'll increase total flood depth. These are all bad things, okay? And they were just completely ignored by the DOE climate report. So cherry picking, focus on trends and number of TCs, a quantity nobody claims is changing. This is a straw man. It's just a waste of time. They acknowledge storms are getting more intense. Great. Some common ground. That's bad news, by the way. Factually wrong claims about rainfall and storm surge. And they ignore many of the other factors in physics that inform the future. And the bottom line is, and there's a strong consensus of this, climate change is making any hurricane that forms more destructive. All you need to know is the sea's rising. Sea's rising, you're getting more flooding from storm surge. Bad news, okay? All right, so let's go on to precipitation. All right, I'll get through this in 1 minute. So, chapter 11.4, heavy precipitation, 11.4.2, observe trends. They conclude the frequency and intensity of heavy precipitation have likely increased at a global scale over a majority of land regions with good observational coverage. Now, if you look at 11.4.2, those are the papers they cite. It's 130 papers. It's a pretty short section, but they're citing all the literature. If you look at the DOE report, that's what they cite. And I'm going to flip back and forth. If you are keen, you will notice a difference. And again, the problem here is that they make no effort to engage with the scientific literature. I mean, why should we believe the one paper they cite over the 130 papers that come up with a different conclusion? Okay? Now, I asked my colleague, John Nielsen Gammon, Texas State climatologist, someone widely respected. Dr. Christy knows him. I predict Dr. Christy would even say he's an extremely reasonable guy. I asked him for an email comment. This is what he sent me. Chapter 6 summary. The sole sentence on extreme precipitation. Some increases in extreme precipitation events can be detected in some regions over short intervals, but the trends do not persist over long periods and at the regional scale. False. The statement appears to be based entirely on the work of McKitrick and Christy prior to and in the DOE report. As a general rule, because extreme precipitation is by definition rare, it is dominated by noise at the station scale. The regional results from the IPCC use thousands of stations, not the few dozen that McKitrick and Christy use. So the trends they detect are much more robust. My study, Jorgensen and Nielsen Gammon 2024, went back nearly as far as McKitrick and Christy for the south and southeast, but used hundreds of stations. It was able to detect and quantify the upward trend in extreme precipitation. Works by Dan Wright and others have shown that an upward trend in extreme precipitation is detectable using large data sets over the central and eastern U.S. So, I mean, this is full of scientific felonies that would prevent it from ever making it through peer review. Very few stations, ignoring 100%, I'm rounding up from like 99.3, 100% of previous literature. They provide no explanation of why all the previous literature is wrong. They ignore our physical understanding of, we understand physically why we should get more intense rain events. The 5-day metric, the IPCC usually uses a 1-day metric for mostly. And, the DOE report is just too weak to contradict the IPCC's conclusions. Thank you.
Okay, I've been asked to address the issue, whoops, why are we back? No, we're back in John's. There we go. To address the issue of how well are the models doing compared to observations, with a focus on temperatures and warming over the past 100 years. The models are important because they are the means by which we can project the climate changes induced by growing greenhouse gas concentrations. And I think it's important to realize that the models are really used to determine response. And what do I mean by that? You might see wonderful animations that are put together by NASA or NOAA of the climate system, and you see the jet stream and the clouds come and go with the days and the seasons, and they look really impressive. But that's not what we're interested in. We're interested in how the climate will change under human and other influences. Because I'm a physicist, I can't resist drawing a mass and a spring. And what we're interested in is not the unweighted position of the spring, the unperturbed climate system, but we're interested in how much will the spring stretch when we apply force to it. For the climate system, the force depends upon time. This is an IPCC graph. It shows the force. Upwards is warming, downwards is cooling. You see the greenhouse gases, mostly important are carbon dioxide, the pink line going up to the present. It starts in 1750, by the way. You see episodic coolings due to volcanic eruptions, the downward spikes, and you see a large amount of relatively slowly varying cooling due to aerosols and so on. It is the totality of these that are being applied to the climate system and that we have to understand the response. Doing that through the models has a number of problematic features. First of all, the forcings, the numbers shown here, are only about 1% of the natural flows of energy through the climate system. So this is a tiny tickling physically of the climate system. Of course, it might induce temperature rises that are enough to give us concern, 3-4 degrees worth of rise, but still, from a physics point of view, you're just tickling the system. We build these models by covering the Earth with boxes, typically 100 million boxes, and we move them through about 100 million time steps to describe some centuries worth of climate. And what you do when you do this is you discover that the world has about 50 different models put together by different groups. They disagree among themselves and they disagree with the data. There are various reasons for doing that. I'm not going to go through the details, but just to say, when people say models predict, you have to ask which model because they disagree with one another a lot. Let me show you some of that. This is a graph for 37 different climate models put together by groups around the world of how much would the global temperature go up if you doubled carbon dioxide. So this is a measure of the stiffness of the spring, if you like. And you can see that there's a factor of 3 from 1.8 degrees all the way up to 5.7 degrees variation among the models. The IPCC, using the models but also various observational data, says that the best estimate is about 3 and a likely estimate is between 2.5 and 4. You can see that there are more than a few models that are well above the IPCC estimate and deemed to be just too sensitive to be plausible. That should give you pause. The best modelers making their best attempt get it wrong, too sensitive about half the time. Let's see how it compares to the time history. This is the rate of warming from 1980 to 2024, so about 45 years of surface warming. How fast did the globe's surface warm? The individual red bars are the models, the different models. The yellow bar is the average of all of the models, and the blue bar is the observations. So again, models much too warm for the surface warming over the last 45 years or so. When you look at the time history, it gets even worse. The panel on the left shows the temperature change from the late 1880s up until more or less the present. The black curve is the observed warming, and the different traces are the different models. They're color-coded according to their sensitivity, the blue models being less sensitive, the brown model being more sensitive, and you can see it's pretty awful. The models do a terrible job individually of describing the variation of the global temperature over the last 140 years. If you focus in on just the last 40 years, as shown in the right panel there, it gets a little bit better, but it's also clear that there are some models that are just way too sensitive. When you try to segregate the models according to how sensitive they are, the first column is the low sensitive models, the middle column, the medium sensitive, the ones on the right are high sensitivity, and then going across in the rows, 4 different data sets. If you just focus on the lowest one, you get the point. You can see that it is the least sensitive models that do the best job of reproducing the historical observations of the temperature. So there's good reason to believe the climate is not as sensitive as the majority of the models predict. That was about surface temperatures. The models also fail in the upper atmosphere. Here in these graphs, the red are the different models, and the blue are the observations. Upper left panel, middle troposphere globally. Upper right panel, middle troposphere in the tropics, and similarly lower troposphere in the lower panels. The lesson to take away is twofold. One is the models are quite variable in what they predict. It's not just physics, because they give different answers. If it were just physics, it would give only one answer. And secondly, almost all of the models are inconsistent with the observations. If you go up into the lower stratosphere, here are 42 different models looking at the trend. The histogram shows the different trends over the last 25 years. And what's interesting is that the models all predict that the lower stratosphere should be cooling as it was from 1980 to 2000. But in fact, what the observations show is that for the last 25 years, the lower stratosphere has been warming. There is some fundamental misunderstanding at a level that matters in the models about how the atmosphere warms, and probably having to do with convection and clouds. Of course, the proponents of the consensus view will say this is just natural variability, and for the last 25 years, the climate's doing something that we didn't expect. But of course, they'll perfectly believe what happened from 1980 to 2000 and say, aha, the models are right. There's a lot of inconsistency in how people compare the models with the data. It's an even worse description of finer features. This is the trend of observed temperatures in the US Corn Belt, about 11 states, over 50 years. The red, again, are the different models. They have names, as shown on the bottom. And the blue is what's observed. This was criticized extensively in the paper that Andy and Rob Kopp put together. Here are some of the criticisms that they leveled. You guys selected a region where the models do worst. No, we selected a region that is agriculturally most important for US agriculture. Global analyses show that models do quite well at simulating the magnitude of historical warming, they said. No, don't change the topic. Okay? It's the regional trends we're talking about here. Explain why the models do poorly here, they urged us to do. Explain how this does not apply anywhere else on the globe. Again, do not change the topic. And is it unforced variability, as you say, or is it intensive agriculture, as you say elsewhere in the criticism? And then they say, finally, use a multidimensional ensemble approach that demonstrates the models do better if you include the uncertainties in the models. Well, if you do that, it broadens the uncertainty so much as to be almost essentially useless. Let me show you what they mean by that briefly, and then I'll wrap up. What's plotted here is a number of different models. On the horizontal axis is the global trend in temperature from 1981 to 2014. The gray band is what's observed, and the vertical axis is the sensitivity. And you can see that it is the least sensitive models that agree with the observations the best. And as the models get more sensitive, they give too large a trend. Well, what is urged by the critics of what we wrote is that any given model does not give just one answer. Depending upon how you set it up and you start it, you can get a whole range of answers as shown here. Those horizontal lines are the results for a single model run under different conditions. And so they say, you know, if you look up at one of these high sensitivity models, the fact that I can find one starting point that actually agrees with the data is enough to validate that data, that model. Of course, that doesn't sound right at all. In fact, they recommend at one point finding the least instance in each model and saying that makes all the models okay. I don't think that would pass peer review, at least among the peers I know. Let me close with a taxonomy of the kind of criticisms that are leveled in the report about models compared to rarely do you see, although sometimes, the methodology that we used was incorrect. More commonly, they'll say, what you said is correct, but here's some omitted context, here's a non sequitur, like I'll talk about global temperatures instead of regional. Your comparison interval is too small or too large, or your area is too small or large. Of course, the IPCC does this routinely. There's internal variability, as was said by, I think, Mark Twain. Statistics are the last refuge of fools and scoundrels. In this business, internal variability is the last such refuge. You need to include uncertainties, as we just explained, or here's why the model is wrong. They'll explain why it's wrong, but not disagree that it's wrong. The forcing's wrong, they'll say, or the data are wrong, finally, as you heard Andy say a few minutes ago. Or they'll say it's irrelevant, what you're saying. I'm just going to close with two quotes from primo climate modelers, Tim Palmer and Bjorn Stevens, writing in PNNAS, a refereed report. For many key applications that require regional climate model output or for assessing large-scale changes from small-scale processes, for example, convection, the current generation of models is not fit for purpose. And then there was a paper in 2019, the use of climate models to guide local practical adaptation is unwarranted. Climate models are unable to represent future conditions at the degree of spatial, temporal, and probabilistic precision with which projections are often provided, which gives a false impression of confidence to users of climate change information. I can tell you I've got about 40 years of looking at sophisticated computer models to various applications, and climate modeling is not one of the better fields. And I think I'll leave it at that. Thanks for your attention. Andy.
Okay, so let's talk about climate models. This is a plot of Jim Hansen's 1988 prediction. The black lines are the models. The blue lines are the observations, an observational ensemble. And you see it agrees pretty well. And what you find is that climate models have a track record of getting the answer right. Now, it is true, that's true for CMIP 3 and CMIP 5. It's true that and here's Exxon. Exxon basically had a spreadsheet, and they got the temperature right. Predicting the future global temperature is not very hard. I can do it with 2 differential equations if you want to predict the global average temperature. It is easy to do. It is true, though, that the last generation of models does have some models that run too hot. And so what Dr. Koonin said was right. But what he said that's really unforgivable, I think, is he didn't talk about how this is well known in the scientific community. He's not, it's not the case that we're trying to bury this under the rug. The IPCC 6 Assumptions Report clearly discusses this. This is a paper in Science from my colleague Zeke Hausfather, and he clearly says, the models, we do have a set of models that's too hot. And they give a recipe for screening the models. So if you work on a problem that requires you to have the right climate sensitivity or requires you to have a good temperature, then then you can do it. And so let me just kind of show you this. I sort of threw this together in the last few days. So this is all the models, same time period Dr. Koonin showed, which is 1979 to 2023, 2024. And you see there is a difference. So the blue bars, it's a histogram. So the blue bars show that the models do on average, the horizontal blue line is the model average, and the red line is the Berkeley Earth. There's a difference.
Only 1979.
But some of the models are too hot. We know that. So we can screen them. We can screen them following what the IPCC did, following what Hausfather said, and that's what you get. If you screen them for good ECS, you get the right answer, good climate sensitivity. You get the right answer. Now, the key thing to realize here is scientists are not idiots. Okay, if I'm doing a study that requires climate sensitivity to be accurate, I'm going to screen the models. If I'm doing a study that requires, I'm doing a study of ENSO, I'm going to use the models that have the best ENSO simulations. All right, scientists know what they're doing. So this idea that some of the models are wrong is irrelevant. It is irrelevant. He said that's what I'm going to say, and indeed I'm saying that. It is irrelevant. And I would sort of encourage him, maybe you guys can ask him, what's the implication on the debate of this? What result has come out from models being too sensitive that he thinks has misled the people? Now, let's talk about tropospheric warming. So this is a page shot from the DOE report. This region, the troposphere, the atmosphere, is an important test of climate models, since this is where the signal of anthropogenic greenhouse warming first and most strongly emerges first and most strongly. So that's wrong. That's just wrong. It shows a stunning lack of understanding of the atmosphere. It is not a fingerprint of greenhouse warming. It's just moist convective physics. ECS predicts too much warming. If future climate models were to realistically represent global tropospheric warming, they would likely be less sensitive than even the low ECS members of the CMIP 6 ensemble. That is wrong. Okay, that is absolutely wrong. The models do a good job reproducing the individual feedbacks. There's no reason to think that the models are getting anything about climate sensitivity wrong. I mean, the high models do look unrealistic, but the bulk of the models, especially the ones that are in the middle, look quite good. And there's no reason to think that if you fixed it, you would get lower than the low end. All right, that's made up. So now, let me say that again, what Dr. Koonin said was right. There are disagreements between models and observations in the atmosphere. Again, this is well known. If you read what they say the IPCC always points this out. But the thing you got wrong is the physics of this is extremely well understood. We understand what controls the atmospheric temperature versus the surface temperature. It's just convection, moist adiabatic physics. And the observed model difference has multiple explanations. Dr. Koonin kind of tap danced around that. Oh, they'll say it's the observations. Yeah, it's the observations, or it could be the observations. Oh, he was very dismissive about internal variability. There's actually research showing that. I'll show you a screenshot in a second. Those are literally quite relevant explanations. And again, if he tried to publish that, it would return folded, spindled, and mutilated, because they would say, you've got to talk about these other things. So let's talk a little bit about the observational biases. Satellite temperature record, Dr. Christy's record, has large non-climatic corrections that have had to be applied. Trend estimates are very sensitive to methodology. Published uncertainty estimates, as pointed out in our rebuttal, are often too small. The updates often shift the trends by amounts comparable to the state of uncertainty. And there's lots of papers that talk about the uncertainty. None of these were included in any discussion in the DOE report. Radiosondes, again, I'm not going to belabor this. The radiosondes where they launch balloons that hold thermometers, those are extremely hard to get trend data out of. Lots of possible errors in those. Again, here are all the papers not discussed in the DOE report. Reanalysis. I won't even go into what reanalysis is, but reanalysis are susceptible to drifts and discontinuities, not designed for long-term trend detection. Read the literature. And again, I mean, it's you know, everybody has their own opinion about these things, and anybody can get up in front of a microphone and say whatever they want. And that's one of the problems with this debate. You know, there's no rigor. There's no rigor to it the way there is in peer review. Again, try to get this argument through peer review. It would not fly. I understand Dr. Koonin sounds very convincing. He sounds very sure of himself. His arguments are not good. And you know, he really poo-pooed internal variability. This is actually important, and it's not like we're just making it up. There is literally publications on this, not cited in the DOE report. I mean, I presume they've read the paper. Maybe they have, maybe they haven't. But this is a paper that came out, Pochedley, PNAS, Proceedings of the National Academy of Sciences, and they concluded that the forced response actually agrees quite well, in their analysis, agrees quite well with the models, but there's also unforced variability. I mean, again, they're not just saying it, they actually have an analysis that shows it. And I would encourage, if the DOE report has an analysis that shows it's not important, they show it. They don't have that, okay? All they can do is try to poo-poo it. Oh, internal variability. That's what people who don't know the answer say. No, it's what the peer-reviewed science says. In addition, there's also a forcing bias from biomass burning that also tends to make the models trend to be too high. And in fact, this is a quote from it. Our results indicate that internal variability and forcing uncertainties largely explain differences in satellite versus model warming and are important considerations when evaluating climate models. You know, that's science. The DOE report, not science. You can't just get up here and say, it's not important, and you know, try to, you know, cast aspersions. So let's go over the felonies. These are not misdemeanors. First of all, these are recognized problems. We understand how to screen models that are too sensitive. Again, scientists aren't idiots. It is true some models overpredict surface warming. Again, well known. It is true differences exist in atmospheric warming between the models and the observations. But the cause of this is unknown. You cannot say it's the models without showing me the work. They do not show the work. They have no work. They're just working backwards from a predetermined conclusion. And this is unlikely to be a major problem with models. We understand the physics. We understand the physics of atmospheric warming. The models should do a good job on this. All of our estimates suggest the models do a good job with this kind of thing. And you know, the DOE report is unacceptable. It contains errors and only discusses evidence supporting its preferred conclusion. It ignores all of the evidence that doesn't agree with it. And in fact, this is not, actually I won't go to it. I have a plot from Wally Broker showing in 1975 he was accurately estimating things. Anyway, I will stop here and turn this over to Dr. McKitrick.
Actually, I think mine is just sitting right here, so I'll just go off this version of it. Okay, I want to talk about the economics findings in our report. Specifically, I'm going to talk about U.S. agriculture, climate change and income, climate change and economic growth, and some comments on the social cost of carbon. Now, as a preface, I want to quote from the IPCC's fifth assessment report in 2014 in the economics chapter that concluded, for most economic sectors, the impact of climate change will be small relative to the impacts of other drivers. Changes in population, age, income, technology, relative prices, lifestyle, regulation, governance, and many other aspects of socioeconomic development will have an impact on the supply and demand of economic goods and services that is large relative to the impact of climate change. So it's important to understand the position not just of the IPCC but the economics profession over the decades that I've been studying this is that climate change matters, it has effects, but over the long term these are small relative to just about everything else that drives our standard of living. So talking about climate change in agriculture, there's a couple of different ways of modeling the effect. One is to relate land values to things like temperature and precipitation. And the more recent literature on that would say the warming is bad, that it has a negative effect on agricultural land values. Critics of that literature have said land values embeds too many things unrelated to climate. You should look at the rents paid for agricultural land. And if you focus on land rent models, the evidence is that warming on balance has been good for agriculture in the US. There's another approach using repeat land sale data, and that was originated in France, and the authors there found that warming has been very good for French agriculture. Using repeat land sale, you can factor out all the fixed effects that way. That study, I think, is relevant, but it would need to be replicated on US data to apply it here. Then there's an issue of whether US farmers are adapting to warming. So this was raised in Andy's report that we didn't talk about evidence that US farmers are not adapting as they should, as we would expect them to warming. So I talked to people in the crop insurance and the agricultural economics field. A difficulty there is the US government subsidizes crop insurance now. It's about 60% of the premium is paid by the government, and that has severely worked against farmers engaging in adaptive behavior because they're becoming indifferent to crop failure. So that's an open question about how to get at that issue. Now, crop modeling is a little different. The econometric literature doesn't take account of the CO2 fertilization effect. So crop models can embed the effects of warming and precipitation change and CO2 fertilization. Generally, the results are that warming is bad, but CO2 fertilization is good. Precipitation doesn't really matter too much on a large scale. And a meta-analysis, a large-scale study in 2014 by Andy Challinor in the UK and his co-authors, their analysis was the effects broadly cancel out. The warming and the CO2 roughly cancel each other out. There would be a slight net gain in the simulations from their regression model. In 2017, a reanalysis of the same data set came to a very different conclusion, argued that the negative effects dominate, and that was a very influential study in the interagency working group. However, I was puzzled how you could use the same data set, come to completely different conclusions, so I got the data to try to replicate both sets of analysis and found that the Challinor data set left out about half of the CO2 data. And so I went back to the original sources, found as much of it as I could, put it back in, and then redid the Moore analysis, and their results end up lining up with the Challinor analysis after that, that the CO2 and the warming effects roughly cancel each other out. Even as far as 5 degrees warming, you get an overall, essentially nothing much changes in net yields. There's a more recent study, Hultgren et al., which I won't go into, was brought up in the comments, because they also report extremely negative effects from climate change on agriculture. However, their main focus in all the tabulated results in their paper, they leave out the CO2 fertilization effect. So they're reporting the results just with warming and no CO2 fertilization. You have to dig way into the online supplement to find the combined effects. And once again, it comes out roughly as a wash. So I won't go into that study. Moving on to climate change and income, you could picture an inverted U-shaped relationship if you have temperature on the horizontal axis and income on the vertical axis. The idea has long been there that there's an ideal temperature to live in. And then if you go colder than that, income goes down. If you go warmer than that, income goes down. So you have this inverted U-shape. And that would imply that warming will be beneficial in relatively cold places like Canada and relatively harmful in hot countries. And now that inverted U-shaped picture, it's hard to actually find it in the data, but it's a plausible picture. And the empirical literature on this, it would then say that if you just shift the whole distribution of temperature up, you'll get a mix of positive and negative effects. And one of the authors that contributed to Andy's report, Richard Toll, has a recent survey of literature on this, and his summary was, researchers disagree on the sign of the net impact, but agree on the order of magnitude. The welfare loss or gain caused by climate change is equivalent to the welfare loss caused by an income drop of at most 10%. A century of climate change is not worse than losing a decade of economic growth. It's not nothing. Canada's lost a decade of economic growth, but it wasn't temperature, it was bad government. But this is the chart that Toll has in his paper. And so Richard, in his comments, he objected to the chart that we used in our report and said we should have used his, so here's his, because it shows about the same thing. On the horizontal axis, you've got temperature, and on the vertical axis, you have percent change in global average real income. And these are econometric estimates as well as some modeling estimates. The heavy black line corresponds to about a 1 degree income loss per degree of warming, and that holds up to about 5 degrees. Now there is a range, and the more pessimistic results come from a certain type of study, the less pessimistic are from econometric and modeling papers, but the central estimate is still about 1% income loss per degree of warming up to 5C. It's a one-time effect. So the idea in this literature is a 1 degree of warming takes away 1% of income on average. And that's the kind of mechanism that's put into what are called integrated assessment models, DICE being the most famous of them. And they do show that you get a global loss of income due to warming, but it's relatively small, or very small, compared to the loss of trying to prevent the warming. And so the optimal policy generally involves only modest attempts at abatement, and otherwise you're adapting to the warming rather than trying to prevent it. The latest DICE model, another criticism of the economics chapter was we didn't discuss the latest version of the model in detail. Latest version of the model has a higher loss, 3.1% as of the year 2100, although that's not out of line with other modeling approaches. The thing to compare it to, though, is how much income growth is there by the end of the century? Well, the SSP scenarios that the IPCC is using, at the low end, you've got global real average income has doubled. At the high end, with the most warming, global average real income has grown by 16-fold. So even the poorest countries would be wealthier by 2100 than the US is today. So taking that 3% hit, it's off a much higher income level. It's not like 3% off today's income. Okay, when we look forward in time, we have to think about the processes of economic growth. There was an influential study in 2012 by Melissa Dell at Harvard and her co-authors who put a panel data set together and argued that warming affects the income growth rate too, not just income, but the growth rate. Now, they said it doesn't show up in rich countries, but there's a negative effect in poor countries. And then Moore and Diaz said, okay, if you plug that into an integrated assessment model, because of compounding, you now get a much higher social cost of carbon, a much heavier hit, and it justifies aggressive mitigation policy. So that study, it's been influential, but the subsequent debate hasn't held up that finding very well. So it was replicated on a different data set in 2015 by Burke et al., but then a subsequent reanalysis of the Burke data found or argued that it only shows up if you use a very specific functional form in the econometrics, but more generally, the result is insignificant, slightly positive, but statistically insignificant. Reanalysis of Dell, their own data, there's been a bunch of studies that have corrected some of the empirical deficiencies in their model, and the results disappear. And then on new and more detailed data sets, there's one by Zhao et al. 2018, and then I did one with a grad student that was published last year, and we find that warming has no effect or a slightly positive effect on growth, even in poor countries. And yes, that's my name on a peer-reviewed paper. We actually do publish. John and I publish all the time in peer-reviewed journals, and then we got criticized for citing our own work. So the social cost of carbon I won't go into it in too much detail except to say it aggregates a lot of assumptions that are made at the modeling stage. So it's like a big if-then statement. It's aiming to give you a dollar value of the social damages of emitting a ton of CO2. Obviously, there are a lot of assumptions that have to be applied about the discount rate for the far future, climate sensitivity, assumed damage function shape, emission scenarios, even the assumption of what was the year that the climate was optimal. So the DICE model assumes that the year 1900 was the best climate the world has ever had, and the damage function is quadratic whether you get cooling from that or warming from that. Why 1900? Well, it's an assumption. Uncertainties about all of those issues have to be resolved separately. The calculation of the social cost of carbon doesn't add any information to the debate over those assumptions. And so in the report, well, if I can give you a recipe for a high social cost of carbon, if that's what you want. But I would say that the assumptions that favor a moderate or a low social cost of carbon are the ones that are more secure. To summarize, while the world warmed over the past century, agricultural yields went up dramatically, income went up all around the world, except in a few places, and where it didn't go up, it wasn't because of climate, it was because of communism. And things like climate-related disasters plummeted to very low levels on a per capita basis. So going back to that IPCC quote about the future, that climate will have an impact on the future, but it's going to be small relative to all the other things that affect our standard of living. And I believe that that's been the case up until now, and the best evidence is that that is going to continue to be the case into the future. Thank you.
I think I finally figured this out. It's here. Yeah, that's good. All right, thanks. So to be clear, I'm not an economist. It's always hard to talk about things that are not in your wheelhouse. So I would just encourage you to read this chapter, to make the argument that understates climate risk, ignores risk uncertainty tail outcomes, and the DoE report emphasizes low-end social cost of carbon estimates. And let me just show you one plot from this. So the red bars are the social cost of carbon estimates highlighted by the DoE. The blue bars are all of them. Now, I don't have a problem at all with self-citation. That's a standard academic thing. You cite yourself. But I do have a problem with ignoring other research, and that's really the problem here. This is Richard Toth. He emailed me, when he emailed me this, he said, I believe this is called cherry picking. And if you read their emails, which were released due to litigation, they have high regard for Richard Toth. His opinion is very high, and he actually, if you look at it, the bars have little cherries on it, which I think is adorable. This is not an honest evaluation of the social cost of carbon. It's their opinion, that's fine. But again, if you're writing an assessment, you have to include everything, or you have to explain why you think those estimates are wrong. None of that is in the report. Now, Dr. McKitrick actually said this, and this is actually from the report. He says, 30 years later, virtually the identical point was made by the IPCC itself in the fifth assessment report. And he actually showed this quote: for most economic sectors, the impact of climate change will be small relative to the impacts of other drivers. And I thought, that's weird. That's the fifth IPCC assessment report. He says, evidence since AR5 does not change its assessment. Well, if that's true, why do you not quote the sixth IPCC report? And I knew the answer because I've looked at the sixth IPCC report. In case you're wondering, anybody have a guess why he quotes the fifth and not the sixth?
Because the sixth didn't have a chapter written by economists.
All right, because the sixth doesn't agree with them. Look, that's fine. If you want to make an argument the sixth is wrong, but you cannot skip it. You have to say, the sixth does not agree with me, and here's the reason why. Okay, look, people disagree in academics all the time. The thing you cannot do is simply ignore it and say, we're going to use this 15-year-old result, and we're not going to use this 3-year-old result. All right? You can't do that. And I mean, if he had that, like, here's why we think it's not right. I mean, saying it's not written by an economist, I don't think that's a very good argument, but if they have a good technical argument, let's hear it. They didn't do that, okay? Recent global estimates of the economic cost of climate impacts exhibit significant spread and generally increase with global average temperature. The wide variation across disparate methodologies does not allow a robust range of damage estimates to be identified with confidence. Translation, we have no idea what the impacts of climate change are going to be. I mean, raise your hand if you think economists can predict how much economic growth we're going to have in the next 100 years. Raise your hand. You can raise your hand, Ross, if you think economists can predict I'm not raising my hand. I absolutely don't think economists have any clue about that. They simply can't do it. And I'm not here to bash economists. I'm just saying they have, unlike the climate models, which have a track record of correctly predicting the temperature, economists don't. And in fact, the economic models are made up. This is a very important point. This is a slide from Robert Pindick, who's a professor of economics at MIT. He was giving this in a talk. I screenshot it and I asked it's reproduced here with his permission. Now, let's compare economic models to climate models. Climate models are based on the laws of physics. Conservation of mass, conservation of momentum, conservation of energy, water thermodynamics. The physical system runs on rails, okay? And that's why we can predict the temperature in 100 years. There is no equivalent to economics. The economic models are made up. So the damage function, as he points out in the most popular model, as Dr. McKitrick said, the DICE model, it says losses goes as temperature squared. Why? He says no data, no theory. It's just made up. Why not temperature cubed? Why not temperature to the fourth? Why not e to the t? We don't know. And yet, Dr. McKitrick says this is good enough to bet the future of humanity. We have no idea. There is no academic credibility. I mean, these models are fine for what ifs, for sensitivity tests. They're not fit for purpose, quoting Dr. Koonin.
That's Palmer and Stevens.
All right, okay, Palmer and Stevens, quoting them. These models are not fit for purpose. The models create a perception of knowledge and precision that is illusory and misleading. So Dr. McKitrick said it's only 3.1% reduction in GDP. What are the error bars on that? Plus and minus infinity, okay? Now I asked Richard Toll. You've heard a lot about Richard Toll. Richard Toll is Bjorn Lomborg's favorite economist. I did an event with Lomborg about 2 years ago. It was like, Richard told this, Richard told that. He's the second most cited economist. Nordhaus was the first. So he's somebody that the skeptical side trusts. And I went on Mastodon and I said, the last IPCC report says there's no robust estimate of climate change's impacts on the economy. I was talking about my event with Lomborg. He says, who do I listen to if I want to know what economists agree on and where they don't? He said, there is, of course, no robust estimate of the impact of climate change on human welfare. You know about the range of estimates of future emissions, and you know about the range of response to the climate models, the climate sensitivity. Then put the uncertainties about impacts and adaptation, future technologies, population, economic activities, add monetization of impacts, aggregate over people, time, probability. We don't know what the economic impacts. And I find it just maddening that Dr. Koonin got up here and criticized climate models, models that run on the laws of physics, models that have a track record of getting things right. They're not perfect. And then Dr. McKitrick gets up here and says, let's bet the future of humanity on economic models, models that are made up, that have no error bars. We have no idea what the maximum is. Now, they might be able to make an argument about that, but they didn't, okay? Let's talk about what William Nordhaus, Bill Nordhaus, Nobel Prize winner. I have used the metaphor that climate change is like a vast casino. We are rolling the climatic dice. The outcome will produce surprises, and some of them are likely to be perilous. The message is that we need not roll the climate dice. There's time to turn around and walk back out of the casino. That is not what they're telling us. They're telling us to roll the dice on humanity. He further says, technological change raised humans out of Stone Age living standards. Climate change threatens, in the most extreme scenarios, to return us economically whence we came. Again, we don't know. I'm not saying it's going to happen. What I'm saying is they can't say it's not going to happen. Their numbers are fiction, all right? And that's what all the economists know. I could write an economic model. Give me 20 minutes with Excel spreadsheet, and I'll give you a model. But the question is the model any good? And you talk to economists, they run their models, and most of them will say, yeah, but of course, we don't know if these numbers are good. They're good for other things. They're not good for actual predictions that you can set policy on. So again, the felonies in this section are large: cherry picking, social cost of carbon, misrepresentations, omission of contrary data. And again, I can't tell you how maddening it is that they get up here and insult climate, not insult, they're not humans, but they cast doubt on climate models, physical models, and turn around and say, but these economic models are perfect. Okay? No, do not buy into that. That is not correct. All right, so, and I asked, again, Richard Toll, climate economists, does any economist think that economic model estimates are good enough, they should guide our policy response? He says, no, they're not good enough for that. Estimates of the marginal cost of the first and second best climate policy vary by 2 or 3 orders of magnitude. Credible published estimates of the social cost of carbon vary by 3 or 12 orders of magnitude. You go and say, I think you should interpret cost-benefit analysis of climate policy differently. Almost everyone agrees the optimal policy starts slowly and then accelerates. No one agrees on the rate of acceleration. Almost everyone agrees 100% emissions reduction is hard to justify. I'm not going to get into that. But the point is, this entire thing about economics is just fantasy. It's fantasy. Okay, we have no idea how bad climate change is going to be. Absolutely not. All right, let me summarize. I'm going to sort of summarize my 3 talks. The DOE is not a credible scientific document. It could not survive peer review. It violates most, if not every, norm of science. There may be some norm of science it doesn't violate if you think hard enough. It is a political document designed to support rolling back of the danger finding. We know that from the emails that were released. It was produced by a DOE process that was corrupt. They violated laws, they violated acts. It was not peer reviewed. The writing group was set up, designed to get a particular response. And the other thing about it is, if you ask about climate skeptics, these guys are the gold standard. This is it. These are the best climate skeptics in the world. And if the DOE report is the best they can do, then the red team, blue team exercise has reached its conclusion. There is nothing in climate skepticism. These guys are the best. Their report is awful. It violates every norm of science. It ignores, their arguments just don't hang together. So in that sense, the report was a success. It actually demonstrated that there is nothing to climate skepticism. Climate science is robust. It's probably, in fact, the most robust science in the history of humanity because of the economic consequences. Anyway, I look forward to the conversation. So I guess we'll answer questions. I think some people, I won't point fingers, went over time. Maybe it's me.
We just have a few minutes for questions, but I was going to kind of follow the lead here from before. There was a question teed up to Steve about the relevancy point. So Steve, why don't you start with that, and then we've got time for a couple questions. So as you're answering that, Steve, if there's questions, please put your hand up and we can call on folks. But
So the question, if I remember right, is what was the practical import of having many, 40% of the climate models being too sensitive? And your statement, Andy, that it was well known in the scientific community, indeed, true. But what matters is not the knowledge in the scientific community. What matters is the knowledge among the public, in particular the decision makers. The presence of hot models allowed people to exaggerate the impacts, alleged impacts or possible impacts of greenhouse gases. The scientific community failed people like you, Andy, and people even more credentialed than you. Did not stand up and say, no, that's not correct. The climate crisis was exaggerated with the consequence that society ran down a rabbit hole of rapid decarbonization, deindustrialization of countries, rapid increases in electricity prices and degradation of the grid, scaring the bejesus out of young people about an impending climate catastrophe, and retarding the energy access and hence economic growth of more than half of the world. So yes, scientific honesty has consequences, Andy, and the climate community has failed to accurately represent the situation. The DOE report attempts to right that injustice.
Yeah, no, I mean, that's bullshit. Sorry. I said I wasn't
Andy,
I wasn't
you
going
know,
to-
you're a
I
tenured
was not
professor
going to
at one of the
profanity.
world's better universities. You should not be using the words like felony or bullshit.
Well, I'm sorry, but it is what it is. Look, the IPCC clearly talks about hot models. Articles are written about hot models. What Dr. Koonin is saying is just this fantasy conspiracy theory about how people have been misled. I mean, you know, the people who are being misled are the people who read the DOE report. That's misleading. It is not, I mean, I can't, I mean, what more can we do? It's in the IPCC report. People write it. Everybody you talk to knows about it. I mean, it's just, you know, are there people who exaggerate? Sure. That's not the scientific community's fault. That is not the fault. I mean, the DOE report is far more egregiously misleading than anything in the scientific community that scientific community has said. You know, and I'm sorry, it is a scientific felony. What you guys did in that report violates every norm. There's no peer review. The way you omitted evidence, you know that would not make it through peer review. You know a grad student turned that into you. You would tell him to go back to his
Andy,
desk.
you just gave a 5-minute disquisition on economic impacts, right? One piece of evidence that you omitted is that since 1900 until now, humans have flourished like never before, even as the globe warmed by 1.3 degrees, about the same amount of warming that the IPCC expects in the next 100 years.
Steve,
I think that is evidence, not persuasive, but evidence not to be ignored, that humanity will see a minimal economic impact of the warming that's projected.
Yeah, I mean, that's a ridiculous argument. Look, correlate, you probably
I did
know
not make an
correlation
argument. I
does
just
not
offered
imply
a piece of
causality.
evidence. Okay.
Look, correlation does not imply causality. Why are humans...
Why do you think the pattern will change?
Look, let me finish this. Why are people healthier today? It's because of the invention of antibiotics. It's because we have satellites flying. So 1900, a big hurricane hit Galveston, 8,000 people died. What would happen if that same hurricane hit Galveston today? Well, we have satellites, we'd see them, they would evacuate. It's not that because the Earth's warming and warming is better, it's because we would see it coming out 5 days in advance and people would evacuate. The city would still get absolutely crushed. So, but I mean, this idea that there's a correlation between well-being and temperature is just, that's just the worst. That's the worst argument. I mean, it's evidence, it's so weak, so weak.
I didn't make
You just made that argument. You said
No, I
it's a
didn't
piece
say
of
there was a
evidence.
correlation. I said despite the warming,
Well.
humanity has prospered. Andy, precision of thinking is real important.
Look, precision of thinking, I agree. An event like this, it's hard to do. This is why
No, it's not.
This
No,
is
it's
why
not.
stuff like this should be done in writing. Not, you know, these public events are places with no rigor. People can say anything. So that's why you peer review your stuff. And I guess I would ask you guys, you know, the DOE process was incredibly corrupt. Why did you agree to do that? Why did you not insist on other authors? Why do you not insist on peer review?
We did insist on peer review. We went through an internal peer review, and then we wrote it knowing it would go up for public comment. The peer review process was shut down by the environmental groups. We're still waiting for the opportunity to put out our responses to all the peer review comments. It's not our fault
No,
that we had to sit and wait for a
It is
lawsuit
not,
to be
it is not
completed.
peer review. There was an email from Travis Fisher to you guys saying, do not call this peer review. This is not peer
No,
review.
he said the internal
Gents,
review
we'll
should be
wrap it up
called
with
an
this.
internal review.
That's right. It's an internal review. It's not peer review. Anyway, sorry.
Thank you for the spirited discussion to the panelists here. I think a round of applause is in order.
Thanks, guys.